Hi, welcome to the Unit 1.5 Foundations of Chemistry video. In this video, we're going to explore the second half of key question number 2, which is analyzing matter. Just like with all video notes, you're going to annotate. There's also an optional additional video that is linked in this assignment in case you would like more help. Alright, so in this unit, some of the things that we've been looking at are chemical reactions, and chemists perform chemical reactions. And when we do, we utilize stoichiometry to help us determine how much of each reactant we need, what's our limiting reactant, and then use our limiting reactant to find our theoretical yield. Similar to the lab that you did earlier this week. Once you have your product, however, it's also important for you to analyze it because sometimes reactions don't go as well as you would hope. So you want to make sure that you have your product, and you also want to make sure that it's pure. One technique that we utilize to analyze our product is something called elemental analysis. And what it does is it tells us the percent of each element in a molecule by mass. And this image here shows what an elemental analysis machine looks like. If you're curious, you can do some research in terms of how they actually work. We won't cover that in this video. Okay, so you're this creepy looking scientist and you're trying to figure out, is it your product? So how does elemental analysis help you determine whether or not it's your product? Elemental analysis is used to find the empirical formula of a molecule, and it does that through mole ratios. And once you have your empirical formula, you could use that to determine your molecular formula and also match it with potential molecules that would fit with your sample. So if, for example, you determine that the empirical formula you got from elemental analysis matches the empirical formula of the molecule you hoped for, that will be supportive evidence that you have made your product. If it doesn't match, however, then that would be evidence to suggest that you did not make your product. All right, so how does this work? We're going to do a quick overview of the process before we look at some examples. So when you get an elemental analysis sample, it sort of looks like this. It tells you like the percentage of carbon, hydrogen, oxygen in this example. And then from here, you're going to utilize that information to get your mole ratios. So remember that these percentages are percent by mass. And from that information, you can convert the mass to their moles and get the mole ratios of each element. So for this example, this would translate to 3 moles of carbon to 6 moles of hydrogen to 2 moles of oxygen. Once you have the mole ratios of the elements in your sample, you can then gather that information into your empirical formula. So you'll have your empirical formula here would be C3H6O2. And again, that just comes directly from the mole ratios. If you know the molar mass of your sample, you can use that to get the molecular formula. And once you have the molecular formula, you can match it to a specific chemical or compound. You can also match it using the empirical formula. It's just that it's a greater leap. Okay, just want to show you what an elemental analysis sample would look like. This is sort of the report and the spectra that you would, not spectra, but the image that you could get back if you submitted elemental analysis. It's important to know that these percentages are percent by mass. All right, so we talked about this process. Now it's time to look at an example to see how do we go from percentages all the way to the empirical formula and then all the way to the molecular formula. There are multiple steps to do this. So one way to memorize this is through a poem that my high school chemistry teacher taught me. The poem goes, percent to mass, mass to mole, divide by small, times to whole. And maybe you want to make this more of an upbeat hip hop, so here we go. Percent to mass, mass to mole, divide by small, times to whole, hey! Okay, I'm sorry, I'm from the 90s, so that's exactly how I would have done it. But anyway, this is a great poem and a great technique for memorizing the steps in elemental analysis. Let's take a look. Okay, in example problem 1, according to elemental analysis, your unknown hydrocarbon is composed of the following elements: 48 28.6% carbon, 8.16% hydrogen, and 43.2% oxygen by mass. What is the empirical formula of your unknown? All right, we're going to take the key information, which is the percentages by mass, and we're going to do our work on a separate document. You're going to be sure to write down the work that you see here on this on your packet. So if you need to pause the video, do so now. The first thing you'll notice is that I set up the information into a table. And in the first column of the table, I have the 3 elements, and then the next thing that you see, the next column is percent. That's followed by the mass, followed by the moles, followed by divide by small, times the whole. So each column is a piece of the poem. Okay, so I'm going to enter in my percentages next to their appropriate elements. And then I'm going to show you how we go from percent to mass. So that's real simple. What we do in that case is we just assume a 100-gram sample. If the sample is 100 grams, then the percentages would correspond to the mass in grams. And so all you do really is you just take the percent and make it into grams to turn it to mass. All right, now we need to go from mass to moles. Well, for that, we're going to use moles is equal to mass over molar mass. And we're going to do that for each element. So we have 48.6 grams of carbon, and we divide it by its atomic weight, which you get from the periodic table, and that will give us 4.05 moles. We repeat the same thing with hydrogen. Its mass, which is 8.16 grams, and divided by its atomic weight. And that will give us its mole, 8.10. And then finally do the same thing for oxygen. There's a typo here. This should say 43.2 grams, and we divide it by its atomic weight, which is 15.99. I'm going to go ahead and correct that right now, just to make sure that we are clear about what we're doing. Okay, sorry about that, guys. Okay, so now that we have the moles, the next thing we need to do is, for our next step, it says percent to mass, mass to moles. Next step is divide by small. So what do we mean by that? What we need to do in that case is we need to find the smallest mole value to divide all the other moles by. You may be asking why. The reason is we're trying to get to our molar ratios, and in order to get to the molar ratios, you need to divide each mole by the smallest mole that's there. And in this case, it's the mole for oxygen that has the smallest value, 2.70. So once we identify our smallest mole value, we're going to divide all the other moles by that value. So the moles of carbon, 4.05, we divide it by 2.70. The moles of hydrogen, we divide it by the 2.70, and we do the same thing for oxygen itself. This will give us our molar ratio. So right now the molar ratio of carbon is 1.5, hydrogen is 3, and oxygen is 1. Well, wait a minute. We don't use decimals in our chemical formulas. So now this is for the last step. Because we have a decimal here, we're going to have to do the last step, which is multiply to a whole. And it's very helpful when you're multiplying to a whole to think of things in terms of fractions and not decimals. So you notice the only decimal that we have is this value here, which is 1.5. So we need to multiply this number by the smallest value to turn it into a whole number. Whenever you see a 0.5, you should be thinking of a half, 1/2. And the smallest number we can multiply a half by is its reciprocal, which is 2, to turn it into a whole number. So that means we need to multiply this by 2, and whatever we do to the carbon, we must do to the hydrogen and oxygens as well. So we multiply all of the mole ratios here by 2 to get them into whole numbers. And that gives us 3, 6, and 2. We'll plug in all of these mole ratios into our chemical formula to get the empirical formula, C3H6O2. And again, these numbers came straight from our work. All right, now that you've seen an example problem, it's your turn to try with the CFU. So take a moment, pause the video, and do your work on your paper. If you need to go back and in the video, if that's helpful for you, please do that. When you press play, the answer will be revealed. Okay, so let's take a look at our work. The same sort of thing again. This setup is super helpful, so I would strongly encourage you to do it. All right, so percent to mass, we're going to just go ahead and convert the percentages into grams. Mass to moles, we're going to use the equation moles equal to mass over molar mass to get our moles, and here they are. And then we need to divide by the smallest value, so we need to identify which one of these moles is our smallest, and two of them, turns out carbon and hydrogen both are the smallest numbers. So we divide everything by those numbers, and then that will give us our mole ratios. In this case, we end up with a decimal 1.33, so we need to multiply that by a number to get all the numbers to be whole numbers. Whenever you see something like 3,3, you should be thinking of the fraction 1 over 3 or 1/3. The smallest number you can multiply that by to get it to be a whole number is its reciprocal. The reciprocal of 1/3 is 3 over 1 or just 3. So we're going to multiply everything by 3. And when you do the math here, this should technically be like 3.99, which you're going to round up. Whenever you're close to a whole number, you're good. That's what you're going to use. Okay, so here we have our mole ratios. We go ahead and plug it in and get the following empirical formula. C3, because there's 3 carbons, H4, 4 hydrogens, and O3. Okay, so now we're going to move on to example problem 2, which is using the empirical formula to get the molecular formula. There's one correction you need to make in this example problem. On your packet, it says 108 grams per mole as the molar mass. You want to make sure that says 148. Okay. So let's look at this problem. If the molar mass of your unknown from example problem 1, so this goes back to the example, is actually 148 grams per mole, what is its chemical formula? Now, in order to help us do that, let's go back to understanding what molecular versus empirical formula is. So the molecular formula is the chemical formula for the entire molecule, whereas the empirical formula is the chemical formula with the smallest whole number ratio. So how do we go from the molecular formula to the empirical formula? Let's recap. What we would do is we would look at for a common factor in the subscripts. So looking at this first example, the common factor here is 2. So we would divide all of the subscripts by 2. In the second example, the common factor is 6. So we divide each of these by 6. And that will give us our empirical formula. In this case, for both molecules, it's CH. All right, so in order to go in reverse from the empirical formula to the molecular formula, we need to figure out what this least common factor is, the numbers here in red. So how do we find the least common factor? The easiest way to do it with their molar masses is to take the molar mass of the molecular formula and divide it by the molar mass of the empirical formula. That works out because whatever you scale the empirical formula up by to get the molecular formula, whatever this factor is, the same thing will happen to the molecular formula. So if you calculate the molecular formula for CH and compared it to the molecular formula of C2H2, you will notice the molecular formula for C2H2 is double that of CH, where the molecular formula of C6H6 is 6 times that of CH. All right, so we're going to use this equation to help us with example problem 2. So I just put up here the empirical formula from problem 1, which is what we're using here. And now what we're going to do is we're going to use this information to get the molecular formula of our unknown. Okay, so we're going to take the molecular molar mass of the molecular formula, which they gave us as 148 grams per mole. So our actual compound has this as its molar mass. So we'll take that number, and then the empirical formula, I use my periodic table to get the molar mass of the empirical formula. Right, once I have that, I take 148 divided by the 74.06, and I get the least common factor is 2. That means I need to multiply all of the subscripts in the empirical formula by 2 to get the molecular formula. Once I do that, I actually have my molecular formula. So here's my work down here, and my molecular formula here is going to be C6H12O4, and once again, I just multiplied each of the subscripts in the empirical formula by 2 to get this answer. All right, so to be clear, the 148 grams per mole is the molar mass of the molecular formula, which remember is not the one with the molecular formula for the actual chemical, the actual compound, and the empirical formula just has the smallest ratios.